Okay, so we're rolling. And today the topic is integration by substitution. It's the last piece of our basic integration piece, and so we're going there. Basically, we've got a function. Take its derivative. We get the derivative. We put the derivative into our integration little machine, and out comes a family of functions. And the reason we say a family of functions is, remember, we've got to do the plus c. Gives us a variety of functions, and that just builds on the fact that we know that differentiation and integration are opposite operations. That's what the second fundamental theorem tells us. So we're going to use that as we move forward with this. We'll come back to this slide very soon. So if I start with a function like this and I take its derivative, I go with, like 5, bring the 5 down in front, drop 1 from the exponent, so I'm going to end up with something like x squared plus 1 to the 4th power. And then chain rule says I've got to take the derivative of x squared plus 1, so it's 2x. Okay? Now, if I take this function and take its integral, because we know that derivatives and integrals are opposite operations, I should just get back the original function. So the antiderivative of x squared plus 1 to the 4th times 2x should be x squared plus 1 to the 5th power over 5 plus c. Okay, and the question is, well, what happened to the 2x? Well, it went back from whence it came. It showed up because of the chain rule, so now since we're working in reverse, it goes back to where it came from. All right? All right. So let's try it again. If we have something like this, something to the 3/2 power over 3, when I multiply the 3/2 by the 2/3, it goes away, so I end up with x cubed plus 1 to the 1/2 power. Chain rule says you've got to have the derivative of x cubed in there. X cubed plus 1, which is 3x squared. If I now take the antiderivative of this thing, I should go back to that original function again. So this turns back into x cubed plus 1 to the 3/2 divided by 3/2, which we all know is the same as multiplying by 2/3 plus c. Question is, well, what happened to the 3x squared? Well, it showed up because of the chain rule. It goes away because we're working in reverse here, so and back from whence it came. Okay, you don't need to draw the cartoons, but you want to have the general idea. If I start with something like this, okay, something half of whatever this is squared, so the derivative of something squared is 2 something. So tan x plus 3 to the 1st power, 2 times a half, drop the exponent down. I've got to have the derivative of tan x, so that's secant squared x. And so when I integrate this function, I end up with the original thing back. So 1/2 tan x plus 3 squared. So again, so it's like the chain rule in reverse, because the secant squared showed up because of the chain rule. When we're working in the other direction, it goes away. Okay, it goes backwards, goes back from whence it came. So it's like the chain rule in reverse. Okay, just to go back to that, you get it now? Okay. So differentiation and integration are interdependent. So in order to be able to do some integration, we're going to have to be able to recognize derivatives. And patterns are helpful when solving problems. So there's a couple of big ideas from this unit, and they're going to be really important as we move forward, because today it's all going to be about patterns. You get the pattern. Okay? So if we were to try to integrate something like this, okay, what I've got is I've got some function to the 3rd power, something cubed. And then outside of that, I've got the derivative of that something. The derivative of 3x squared plus 4 is 6x. Okay, derivative of this is that. If I have that sort of situation, I can integrate it because I recognize the pattern. It's the pattern that we've just kind of been playing with, that I've got something to the 3rd and the derivative of the something. This is going to turn into 3x squared plus 4 to the 4th power over 4 plus c. Okay, if you don't believe me, take the derivative of this, and you'll get that because of the chain rule. 4 down, 4 cancel, to the 3rd power, chain rule makes 6x. So where's the 6x go? Well, it showed up because of the chain rule. It goes back because we're working in reverse. Just looking for that pattern. We're looking for the pattern that says you get something raised to a power, the derivative of the something outside, and we are golden. Okay, like this one. Okay, we all know immediately that we never write anything like that. We want that to be to the 1/2 power. Okay, so I've got something to a power. Outside, look, that's the derivative of 2x to the 4th minus derivative of 2x to the 4th minus 8, right? We've got 8x cubed, what that says, but anyway. So when I take the antiderivative of this, I'm just going to make it 2x to the 4th minus 8 to the 3 halves over 3 halves, which is the same as multiplying by 2/3, plus c. Okay? And again, if we take the derivative of this, that 8x cubed is going to show up because of the chain rule. Since we're going antiderivative, it's going away because we're doing the chain rule in reverse. It goes back from whence it came. I'd write that down. It goes back from whence it came. It's very British sounding. It wasn't British sounding at all, but picturing the British accent. Okay? So here, we got something to a power. Do I have the derivative of that something? Almost. I almost have the derivative of x cubed, right? Derivative of x cubed is 3x squared. So what I'm going to do, I'm going to say I don't have it. I'm going to make it so. There we go. Put a 3 in. Can I put a 3 in? Can I just multiply randomly by 3? No, I can't. But what I can do is I can multiply by 1. So if I multiply inside the integral by 3 and outside the integral by 1/3, that is the same as multiplying by 1, right? 3 times a third. See how tricky that is? So now I've got the thing I'm looking for. It's something to a pattern. I've got the derivative of that something. So I can just do the antiderivative. And so this turns into x cubed minus 4 to the 3rd power over 3. The 1/3 is outside the integral, so it's a constant. It's coming along for the ride. So I've got to have it there. So this turns into 1/9 of x cubed minus 4 to the 3rd power plus c. Again, if you took the derivative of all this, we'd get back to the original thing, all the stuff in black. The 3rd and the 3 wouldn't be there, but the derivative of this thing is x squared, x cubed minus 4 squared. Okay? What I call that, because we put something in and we take something out, as we move through, we call that the calculus hokey pokey. Okay, put a 3 in, you take a 3 out. Okay, as Elmo would say. Okay, so the Elmo calculus, you put 3 in, you take 3 out. It's just a 1 in, which always helps you out. You do the integration, yeah, the constant c, that's what it's all about. Okay, so that's the whole story on that. Put a 3 in, you take a 3 out. Okay, that's just 1. So, calculus hokey pokey. It's a little known calculus trick from throughout the world. So this one is going to sort of work in the same way. I've got something to a power. The power is the 1/2 power. I've got almost the derivative of that outside. What do I need to make it the derivative of what's outside? Yes, that's right. I need a 10. So I put a 10 in. I take a 10 out. Okay? Multiply by 10, divide by 10. It all works out. So now I've got the thing fit in my pattern. The 1/10 is coming along for the ride. I do my exponenty trick. 5x squared plus 7 to the 3/2 power. 3. Okay, instead of dividing by 3/2, I'm going to multiply by 2/3. Not going to forget the plus c, and then I'm just going to make it look nice. So this is going to be probably 1/15 of 5x squared plus 7 to the 3/2 power plus c. Okay, just looking for that pattern. We have something raised to an exponent. We have the derivative of that something outside. Okay, where's the 10x go? It goes away the same way it would show up when I did this, when I did the derivative of this. And, oh, it works with sines and it works with cosines. So in this case, what I need is I need to have the derivative of my argument be part of the situation. So the argument's 3x. What's the derivative of 3x? 3. Do I have a 3? No. I can get me a 3. Here's my 3. 3 in, 3 out. Pokey accomplished. Okay. What that turns out to be then is the 1/3. Come along for the ride. What's the antiderivative of sine? Well, it's negative cosine of 3x. And then plus c. And look, we're done. Okay. If I were to take the derivative of this little thing here, taking into account chain rule, I would get what's the original problem in black. Okay, the 3 and 3 in out, and wouldn't make a difference. And again, I can do that because that's just like multiplying by 1. We can always multiply by 1. Okay, oops, there's that. And then those are them, and there's this, and there's that. And so we're just looking for patterns. Okay, remember, this whole integration stuff is about patterns. It's got to be one of the patterns on the card, and we can, work with the extra little piece. as we just hokey pokey it, or it just happens to be there, something to the power of a trig function to something, and we need the derivative of that piece outside. So flash through all those. I think that about does it. Okay, we'll leave you with Elmo's picture. It's almost nice. Okay, so that's the calculus hokey pokey. Got questions? Happy to answer them. Thanks for watching. Thanks for listening. Thanks for writing things down. Talk to you soon. Bring your questions tomorrow. Hope you learned something.